So for the next presentation, it's Crossing the Valley, as you can see, and it's by Dr. J. Meal. Oh, Mr. J. Meal, sorry. I'm screwing this up. J. Meal is Vice President of AI and Chief Data Scientist at SAIC, where he leads AI technical strategy and oversees solutions that enable rapid decision-making at scale in support of multiple intelligence disciplines. Jay is a recognized subject matter expert in the application of machine learning to analytical tradecraft, all-source intelligence, open source intelligence, and C5 ISR. He also serves as a technical advisor to numerous intel organizations within the IC and DoD, and advises congressional committees on topics related to AI. Welcome to the stage, Mr. Meal.
Thank you. Appreciate it. So, hey everybody, good afternoon. Thanks for attending this. Mine will definitely not be as interesting as the human-robot teaming. There's no way. Just want to say the bluff to my bio is I deal with tons of different problems and lots of different very special data and try and temper expectations most of the time. I feel like a therapist more than I feel like a scientist. But that's what I do. I deal with the operational realities and how we cross, the valley to go from something that was, a research tool or a lab production of some type of really neat model into an operational setting. And so that's what I want to talk about today. So I'm going to start by giving you our definition of operational AI. And the reason why I say our definition is there's almost as many models out there as there are for definitions of artificial intelligence and what it is. So instead of trying to define the type of model or the type of technology or how it's working, we define operational AI simply. I spend all my time, I have the best job in the world, I spend all my time with the analyst, the operator, the warfighter, down on the ground, solving hard mission problems. So our definition of operational AI is threefold. The first thing is everything that we put out and that works in the field has to reduce the cognitive load on the operator. Whoever that user is, it's got to reduce the cognitive load. The second thing is it has to drive a faster speed to decision. Why are those two things separate? Because sometimes there's doctrine and policies and real-world procedures in place that can lead to a faster decision but can't necessarily change workflows or different types of TTPs that are already in place. So we say lower cognitive load and faster speed to decision. And the third thing ties right back to the last talk, and that is a proper human-machine team. And that is the human and the machine working together under the concept of a shared mental model to understand a mission and to solve a problem. Now, I will tell you, like I said, there's lots of definitions of AI. There's lots of different types of AI. I deal every day with commercial, proprietary, homegrown, and open source models that do all different things. I'm here to tell you that there is no one model that will do everything. Not one deep learning model, not one large language model, not one statistical machine learning model, which everybody has seemed to have forgotten about because regression is actually the easiest thing to do to get some of these answers. And not future things like world models. So you have to get to a point where you can tie models together. So what I want to talk about today, and the way we're crossing this sort of valley, is something that we call the model control plane, or composable intelligence. And the idea behind the model control plane is if no one model itself can solve real mission threads, then how do we bring all of these different types of models together, the open source, the commercial, the proprietary, the homegrown, right, that take different inputs and different data types and different feature sets and different weights and different modalities and things like that, and chain them together into a system of systems. And in fact, I would proffer that going forward, it's not about how much power the model has, how well the model's been trained, and what the model actually does in terms of making sense of the world. It's more about how we tie multiple models together into these model of model systems, these AI system of systems. And so that's what we're trying to do. And a lot of that goes back to things like observability, explainability, the shared mental model that we're talking about, and making sure the human understands how these models all work together. So the concept of the model control plane is, how do we bring all this together to solve mission threats? So I'll give you an example. I tend to use this one. It's a pretty reductive example, but I think you can see it in your head. If I was on a mission and I had to find a target in the middle of a large body of water, and then I had to do something with that target, I have to use all different types of AI models to sense and make sense of the environment, right? I might have a perception model that's looking at electro-optical or looking at, imagery from overhead. That might tell me what the boat looks like, right? Then I might have to cross-reference that with some type of RF classification model that looks at spectrum and takes that type of input, and maybe I can confirm what that boat is. And then maybe if I need to, if there's a higher threshold, maybe I have to have another model, like a language model that can sift through lots of intelligence reports or information about that particular platform and give me more information. And then if I want to generate a course of action, I might have to have an optimization model that does some type of optimization work and can understand all that inference that had come in before it, make sense of it, and then give me the proper course of action. So the way to do that is tie these models together and build a system of systems. And we've broken this out into sort of 3 layers. And I apologize, I don't have a drawing. They don't pay me to draw. I think I failed kindergarten coloring. I can't color in the lines. So conceptually, here's how the model control plane works. At the macro level, it's designed to take a model of model approach and tie all of those different specific modality models together to help sense and make sense of whatever it is the problem that they're trying to solve is. At the micro level, each one of those models is like a toddler, right? It has to be individually managed and handled. So at the micro level, we're talking about model lifecycle management. So that is, metrics on the training of the model, the testing of the model. Is it fit correctly? Is it giving the right metrics? Is it behaving the way it's supposed to behave? And then globally, we wrap that in a couple other things. We look at things like adversarial perturbation. Has an adversary tried to do some type of attack on this model? Poisoning, extraction, evasion, whatever it might be. And then also, how are we resourcing this model appropriately? Do we have too much compute for inference? Do we have too little compute for inference? Are we using CPUs when we should be using GPU? Do we care about latency? Do we care about accuracy? Things like that. This is how we tie it all together. And this helps to shape and inform the shared mental model concept that you came up with, because to get back to, I love that you asked that question, by the way. So the concept of if the human needs to understand how the model is making sense and how it's inferring all the information that is coming to it, you need to have that level of observability, explainability, the ability to audit back and understand that, what's happening as it makes its decisions through each piece. And because you've built a model of models approach, arguably, you could have a couple perception models or computer vision models. You could have a couple natural language processing models. You could have a couple, RF models or optimization models or COA generation models. And by doing that, you can build what we call democratic AI or a voting system so that you can get more accuracy at the end to understand, okay, if one model's off, but 6 of them are saying this is a ship, it's probably a ship and one model's got a problem somewhere. And then you can dive deeper and you can understand where that drift is, whether it was data drift, whether it was inference drift, and you can dig deeper and deeper. Okay, so composable intelligence, where does that come in? So this is sort of our next iteration and what we're getting excited about. And I know Bob Ritchie, my counterpart from SAIC, talked a little bit about declarative C2 yesterday. What I would love to get to is a point where we can declare the mission thread that we're trying to solve, and models will be able to understand what it's going to take to solve that mission, and then compose a model of models that will solve that mission thread. To include things like pipelines, to include things like the infrastructure that's needed or the compute that's needed, to include the right perception models, the right natural language processing models, the right optimization models, and tie all of it together for the operator and make it very easy and simple to operate. We're not there yet, and that's going to take some self-supervision, and that's going to take humans really relying on these systems to be accurate, and then having the ability to explain that. And I keep saying explainability over and over again because we don't want black boxes, and I think that's more and more important as we go on. So there's lots of really interesting things happening right across the development space. But what happens on, I tell this to our teams all the time, what happens on a laptop or what happens in a laboratory in a controlled environment is very different than what's happening out in the real world. And we have to understand roughly 80% of what we're putting out into the field today is working with technology that's already, legacy technology that's already out there. Legacy compute, legacy systems, legacy platforms, legacy models. And so the model control plane is that way to bring everything together, string those threads into one place, and to help achieve those model outcomes. Now, someone asked me when we originally were talking about this, actually this morning, they said, well, don't large language models just do this inherently? And I said, no, large language models don't do this inherently. And that's actually something I run into a lot working with folks, in law enforcement, intelligence community, Department of War. Large language models look like they're thinking. What they are is really statistical parrots, right? They're trained on a set of data, a corpus of data, and then that's static. And what I have found a lot of times, and what makes this so difficult, just navigating all the AI stuff, is organizations will spend their resources, their time, their money, their human capital in bringing these capabilities in with the promise to solve these mission threads and solve these problems, because they operated really great in the lab environment or on the laptop, but when they get into the operational environment, they're not trained on the appropriate data. They don't have the appropriate prompts or reasoning or metrics around, we'll say, pattern of life. Why is that? Well, it's because the frontier model companies, while they're spending a lot of money teaching these models to code, they're probably not spending any money teaching it to do pattern of life, right? So these are the types of things we have to think about. So you have large language models, and again, that's just the contextual representation of text and what it's learned, by reading. We have the promise of world models. I think there's a talk this morning about world models. Yeah, very cool concept, right? If a large language model predicts the next best word, and by the way, that's all it's doing, it's predicting the next best word based on what it's learned. A world model is predicting the next state or cause and effect, and that's really cool. And there's lots of applications for that. But even that can't do everything. And then how many people have heard, like, everything is the promise of agents now, right? Everything is agentic AI, agents are gonna do everything. Guess what? Agents need lower level models too. They need to be able to call perception models. They want to be able to call language models. They need to be able to call, optimization models. And so it's those low-level models and the stuff that a lot of people have, those quiet workhorses that everybody has forgotten about, that are the foundations to the control plane, which feed to those higher order models, and then the ability to open that up and allow the human to communicate and understand what's happening with the technology. We're really excited about the future of it. We're really excited about adding things like, the declarative piece and being able to just speak to a model instead of inputting it in a prompt window. But really it's about, to get to true human-machine teaming and to get to true operational AI, you gotta have those three things I mentioned before, but most importantly, you have to have trust. If a human is going to rely on these things in life and death situations, they need to understand and be able to rely on how the models are getting those answers. And in order to have trust, you have to have explainability. In order to have explainability, you have to be able to audit and understand what's happening. And that's one of those big reasons why we believe in the model control plane. Thank you.
Okay, thank you, Mr. Meal. At this time, that's the QR code for the questions. You can ask your question through there, or you can come up to the mic. First question.
So those of us who survived the Cold War era heard all kinds of stories about sleeper cells and all kinds of stuff. Let's put it in real world perspective. Large language models are real. How do I know that that model does not have a poison already in it?
Oh, yeah.
When I'm starting, and even if I'm 100% sure that it was a clean model, how do I detect that somebody has not ingested malicious information that's going to hurt us at the time of need?
I love this question. You've been reading recent research papers. So there have been instances in labs and theoretically in the real world where adversaries have built language models that have, we'll say, hidden agendas for like to simplify that, right? It's not really a hidden agenda because it's not conscious, but the idea is hidden scripts and hidden code in it that no one would ever be able to find, and it would behave normally in a lab environment or in a normal environment. But at some point, it could say, for example, the script might say something like, after the first 100 questions someone asks you about X, start creating something else or start logging the data or whatever it might be. It's a very real possibility. And there's been instances where that's been found. So there are some techniques out there to try and suss that out. But I think a lot has to be understood on that. And the only way to really guarantee that you're not going to have some type of poisoned code base is to build your own language model from scratch in a lab environment that you know is sanitized and it's not touching code that otherwise might have been infected or poisoned. But it's probably never going to be as good as the frontier models because they put so much into those models. Hopefully that answers your question. Yes, sir.
Right. I have, first of all, that was great. I resonate heavily to everything you were talking about there. I think this is the right system design, and not enough people are thinking deeply enough about it. So I really, 2 questions. The other dozen, we can wait until we have the drinks at the event later today. You'll be there, right?
I might move my flight. If I can move my flight, I'll be there. If I
Somebody
can't,
move his flight.
I won't. There's an agent for that. That's going to be the new thing, right? There's an agent for that.
No, so the first one is, I was wondering if, in your design, is it hierarchical? Like, if you remember the old homunculi design, like you have a bunch of AIs, they each have special roles, and then they report up to a higher order one, kind of like the way we do, we do the autopilots, right? You guys know this. How many pilots do we have here? But typically, the autopilot, there's not just one, right? There's usually multiple, and if they don't agree, then they have to call the human. But how much of it is hierarchical, and therefore how many levels are there? And my other question is about the data part of it. Like, how do you verify and validate the data that goes into all the submodels?
Yeah, so
That's a lot. But
2 great questions. Okay, so right now it is hierarchical and it follows a formula we're going to take those low-level statistical models and that can feed deep learning models and that can feed higher order models like agents and then languages and eventually maybe world models. But I want to get to a point where it becomes efficient. So that's where I want agents to be able to say what's the most efficient structure for each, we'll call it like ephemeral mission thread or ephemeral task. But we're not there yet. But I think the key is to have choices across all the models. So it needs to be broad enough that if you're doing active defense on the models as well to prevent things like poisoning and extraction, evasion, and force drift or anything like that, you have to have models monitoring the models, right, essentially, that if one model is way out of sync, the system should be able to say that deviation is way out of bounds, maybe it's a couple standard deviations, what's wrong with that model, and be able to go in and self-diagnose, and potentially it's, an adversary did something, shifted that model, poisoned its data set, whatever it might be, I'm going to drop that model out and replace it with another model.
So hill climbing and annealing?
Yes, yeah, effectively. Yeah. Oh, and the data question?
Oh, yeah, the data.
Oh, yeah, data. I mean, right? It's it's dirty, it's messy, it's terrible, it's in all the wrong formats. But a lot of that really comes down to the pipelines that you build and the infrastructure that you build along the way. I mean, what we most frequently find is that the data is obviously dirty, it's not tagged, it's not associated appropriately. A lot of times the tasks that you want to do, even if you were talking about pilots before, I'm not a pilot, but you might have great flight data off of a platform, but what you don't have is commander's intent, you don't have weather information, you don't have other information that goes with that data. So there's a lot of data enrichment pipeline and cleaning that has to be done, and that can be inside the model as well.
Yeah, I think hill climbing and annealing works with data
Yeah,
too.
absolutely. Yeah. Yes, sir.
Good afternoon. James Croson, Tinker Air Force Base. This is not my space in terms of knowledge set, so I'm learning a lot here at the conference and in this session. But the metaphor you used, crossing the valley, really spoke a lot to me, and I'd like to learn more. Do you have authoritative sources or information that you can point me or others to that is more of not a 101 necessarily, but getting started to understand more about this valley?
Yes, sir. We have some white papers on it that we can share with you, and also happy to send you other information I have. And we won't go into them here, but we've got a couple of great Air Force examples where you look at, specific large language models that couldn't do a task, and then you cross that valley by building it around the control plane, and now it can do things like, dynamic ATO regeneration and things like that off of a frontier model that couldn't do that before, right? So there's just different concepts that you can just sort of unlock capabilities. And a lot of that's around that control plane and the chain of thought and reasoning that you add to it. Yeah. Yes, sir.
Hi there. Sean O'Mahony. I work at the Naval Base across town. I'm not super familiar with AI in that I work in IT and cybersecurity, but I haven't really delved into this. My question is that my understanding of AI is that right now it is very energy and computationally heavy and thus very expensive. And so it makes sense that it would take large companies to build out these training models and plans. My question is, moving forward, is there an expectation that through the cheapening of the technology that it would become easier for people, even on an individual scale, especially people who are not familiar with the technology, to actually build out and train their own AI, and that's just a matter of time, effort, technology advancing? Or is it kind of assumed that the process of training is actually too advanced for most people to do themselves, and that's why it requires the large companies?
Sure, it's a great question. So the process of training is not too hard to do on your own, but it is computationally intensive and very expensive, right? So I work very closely with the NRO, for example. And without getting in specifics in an open forum, you have to start thinking, well, how do I get my large language models to do things and behave in a way that I would want them to behave in the environments I work in? Sometimes that's, size, weight, and power constraints. Sometimes that's very specific data sets. Sometimes it might be an embedded system. And what we found is really the shortcut. So there's three ways you can do this, right? You can build your own model, to your point. You will never be as good as the frontier models that are out there because of all the capital and resources they put into it. You can do something called a specialized language model or small language model, where you take a subset of the weights and biases from those language models and train them on specific sets of data to look at specific tasks or answer specific questions. That tends to have issues with hallucination. There's a lot of sort of subsets of problems around that. The other thing you can do is you could fine tune a model, right? And that means taking a model that's already trained and doing really well, like a GPT 5.1, right? And then I'll put it against my data and retrain those data sets against my data. The problem with that really comes down to your op tempo of like your mission, because that's a static image, right? Once it's trained, you've paid the little bit of money or whatever it is, took the time to train it. But if 5 minutes later your data shifts, you're not going to get the right answers off of it. So the way we found that's most efficient right now is something called retrieval augmented generation, or RAG, which some people might be familiar with. And what that does is RAG acts as like an intermediary between, almost like an agent. It's not an agent, but almost like an agent that's an intermediary with the large language model or the language model itself. And when you pass a prompt into the RAG, it's already connected to the authoritative data sources that you care about, right? And so it knows to pull from that data, and that data could be updated at a 1 second battle rhythm or a 10 second or 1 minute or whatever it might be, but your authoritative data sources, it pulls from there. And then you can couple RAG with something called chain of thought or tree of logic, where you can actually put very, very, very specific patterns of how it's supposed to interpret and solve the problem. So you could actually put in TTPs, you could put in doctrine, you could put in rules of engagement. My really ridiculous example of chain of thought and tree of reasoning is everybody knows what a peanut butter and jelly sandwich is. I literally wrote a white paper on this about peanut butter and jelly sandwiches. So everybody knows what a peanut butter and jelly sandwich is. If I asked each of you to make me a peanut butter and jelly sandwich, you may make it just slightly differently, right? So I can tell a language model that is going to give me essentially a probabilistic or a non-deterministic answer, how to specifically get to that answer so I have more explainability. And so the peanut butter and jelly example is chain of thought would be something like, first get the bread, then get the peanut butter, then get the jelly, then put the peanut butter on one side, the jelly on the other side, smash it together, right? And it's always going to do it that way. And if I had a more complex sort of reasoning that I needed to go through, and I talked about that tree of reasoning or tree of logic, then it might be something like, first get the bread, you could choose white or wheat. Then get the peanut butter, you could choose crunchy or smooth, right? Then get the jelly, you could choose grape or raspberry. And so it's more branching in trees. And you can do that with large language models in natural language right now. So you can actually take a model that's out there, a frontier model that's out there that has never explicitly been, had your data represented to it and never solved a specific mission problem for you. And using RAG and that chain of thought reasoning, you can pretty quickly in natural language get it to answer the way that you want it to answer.
Thank you.
Yeah, absolutely.
I think that was the last question
Okay.
because we want to make sure that you can get to your flight.
Yeah.
Okay. Well,
All right.
thank you so much,
Thanks.
Mr. Meal. Thank you, everyone. So round of applause for Mr. Meal.
Appreciate it.